There's a bit of theory here, and I think I might just leap into the questions, and then I'm going to point back at the theory as we answer the questions. And it would be good for you to read through it at some point, but I will try and bring up all the points as we're going through the questions today. So, central limit theorem. Let's go to question 1. We've got x is a random variable with a mean of 30 and a standard deviation of 10. Now, I really want to point out to you here that it does not say that x is normally distributed. Okay? So there are lots of ways that variables could be, but here it says very clearly by what it doesn't say. It doesn't say it's normally distributed. So that means we cannot assume that it has a normal distribution. However, the central limit theorem tells us the more samples we take, or the more times we observe this random variable, the more symmetric and the more bell-shaped the distribution will become. Okay? So if you're reading the information there, there's no set number, and it says in the first point there, many texts use if n is greater than or equal to 30, okay, that it is sufficiently large, okay. Now we can use that as a sort of starting point, okay. But really, what it means is really the test of normality is the shape of the distribution bell-shaped, okay. So here's an example of a normal distribution. Here's an example of a distribution that is not normal. Okay, that would be a positive skew. Okay, so we've got central limit theorem, mean 30, standard deviation 10. Okay, is x35 approximately normal? Okay, so if I've said to you, provided there's at least 30, that's our starting point, provided there's at least 30 observations, then it's approximately normal. We have x35. Okay, what does that mean? It means we've observed the variable 35 times. Is it approximately normal? Yes, as n is sufficiently large. Okay, so never say yes because n is greater than 30. We'll say yes because n is sufficiently large. Alright, and this is going to be reflective of its histogram. Okay, part B. Find the mean and standard deviation of x35. Okay, so right in the very top box it says if x is a random variable, x has mean, mu, and standard deviation sigma, then xn has mean, mu, and standard deviation of x10. Let's write those formulas out. So the mean of xn is going to be the mean of x, and the standard deviation of xn is equal to the standard deviation of x on the square root of n. And that's what we covered in 9b when we talked about sampling distributions. Okay, so if we want the mean of x35, well, it's going to be equal to the mean of x, which is 30. And if we want the standard deviation of x35, okay, 35 observations of the random variable, it's equal to the standard deviation of x divided by the square root of the number of samples. We've done 35 samples. Okay, so that's part B. Okay, part C. Find the probability of x35 being larger than 32. So because it's asking specifically about variable x35, and we've established that x35 is approximately normal, that's what we established up here, it's approximately normal because n is sufficiently large, we can use a normal distribution to perform this calculation. So you think it's asking, what's the probability of x35 being greater than 32? Okay, and so the calculation we're going to perform, we've got our lower boundary, our upper boundary, standard deviation and mean. Our lower boundary is 32, upper boundary infinity, standard deviation is 10 on root 35. Why 10 on root 35? Because it's asking about the variable x35, not the variable x, and the mean maintains at 30. Okay, and when I put these in my calculator, I like to use both techniques that I've been through with you guys. But I didn't bring my calculator today. Oh, yes, I did. Okay, so I'm just going to go into stats today. Normal, NCD, lower boundary 32, upper boundary infinity, standard deviation 10 divided by the square root of 35, and the mean is 30. So I've got the probability of x being greater than 32 is 0.1183 or 0.118. So 3 significant figures. Now remember, for any normal distribution, for continuous random variables, there is no significant difference between greater than or equal to and greater than. Okay? That only applies when we're talking about whole integer values. That's question 1. Let's move on to question, part D. Is x6 approximately normal? Okay, answer, no, n is not sufficiently large. Okay, you will be tricking this question here. Question 2. Suppose x is a variable. What does all this language mean? X is normally distributed with a mean of 10 and a standard deviation of 3. So we're told the variable x, whatever it is we're observing, is normally distributed. Part A. Is x4 normally distributed? The answer here is yes. Okay? Yes, xn will always be normally distributed if the variable x is normally distributed. Okay, so here we're told explicitly, yes, it's normally distributed. That means xn for any value of n will also be normal. Over here, we're not told it's normal. We're just told it's some variable, okay, with a mean and standard deviation. So we cannot assume it's normality. Here we're told it's normal. Okay, so we're justified in assuming that x4 will also be normal. Okay, so that is, so let's answer part A and B, and then I'll point out where that occurs in our is x4? Yes. And what's our justification? We provide a justification for it. x4 is normal, yes, because x is normal. Okay, so I'm just going to communicate it like that, because x is normal. Okay, what about is S5? Now S5 is the sum of 5 individual observations. Okay, and so I'm going to point out where it is now. If x is a random variable, let's look at the third dot point in our last box. If x is normally distributed, then xn and Sn are normally distributed for any n. So S5 is normal because x is normal. Alright, so yes, we're justified in saying it is for any value n. Okay, let's move on to question 3. And we have those 2 histograms. Let's read the question. The price of smartphone apps have a mean of 89 cents and a standard deviation of $2.42. Okay, so mean and standard deviation. Interpret the variable x50. Okay, so if you were to do x50, that is the mean cost of 50 smartphone apps that you've observed. Okay, so let's answer that. Mean cost of 50 observations, or mean value of 50 observations of smartphone app costs. Change that to value. Okay, so that's part A. 2 histograms are shown below. One shows the variable x and one shows the variable x50. So I'm just going to draw their shapes approximately here. This one's like. Okay, so what do we know from the central limit theorem so far is that the larger n, the more normal it's going to be. Now one of these histograms is x and one of them is x50. Okay, so the question is which one's got a higher number next to it? x50. That's going to be the one that's more normal. Which one's more normal? This one. It's approximately normal. It's not heaps normal, but it's approximately normal. And so we're going to say this is x50, and because its shape is approximately normal, not because n is larger than 30. Okay, I've said that's a starting point for us. Okay. That's a starting point. So we're not going to use that as a rule, but we look at the histogram and we assess it's approximately normal, therefore you would be justified in using a normal distribution for this one. Over here, it's not anywhere near normal, all right? It's a massive skew. Okay, let's move on to question 4. This is a good question, this one. So I might spin this around. And it'll be up there if you want to photograph it a bit later on. So this is what the central limit theorem means, and it's best exhibited in this question. We have Carlton dry stubbies and are normally distributed. The mean volume is 335 millilitres, and the standard deviation is 5 millilitres. Okay, so we're told that they are normally distributed, okay, which means for any value of n they take there, that it will be normal. Part A, find the probability of x being greater than 340. This is a simple normal distribution calculation. We're saying what's the probability that a randomly selected bottle is going to have more volume than 340 millilitres. So let's do it this way this time. NCD, we're going 340, E99, 5, 335. Put that in and you run that, and it will generate the solution for you. E99, 5, 335. I've got 0.1586, which is 0.159. Okay, so the probability of getting a bottle that's got more than 340 mils of beer is about 16%, or just under 16%. Okay, part B. A carton has 24 stubbies, so there's 24 bottles of beer in a carton. Find the mean and standard deviation of x24. Okay, well remember, the mean of x24 is going to be equal to the mean of x. Okay, that is the mean of distribution trumps the mean of any observations that you make. So that's 335. But the standard deviation of x24 is going to be equal to the standard deviation of x divided by the square root of 24. So what's that? 5 on the square root of 24. We'll leave it like that for now. Okay, so that's part B done. We've found the mean and we've found the standard deviation of 24 observations. Okay. Part C. Find the probability of x24 being larger than 340. Okay, so let's do that. We're going probability of x24 being larger than 340. So it's different from this one. Our calculation is almost the same. I'm going to write out the calculation. So that's NCD, our lower boundary is 340, upper boundary infinity. Our standard deviation is the only value that's different, 5 on root 24, and our mean is the same. Okay, so let's calculate that, and then let's chat about why there's a significant difference. Here, when I answer this question, I've got 4.816 e to the minus 7. Okay, so how do you write that with as a decimal number? 7 zeros. So 7 zeros, 3, 4, 6, 7. Put the decimal place after the first one, and then list the numbers 4, 8, 1, 6. So look at the difference in probability between getting a randomly selected beer and then this one here. So what is the difference between them? Okay. The question we're asking, here you're saying you're grabbing any single beer at random and saying what's the probability of it being larger than 340 mils. The calculation we're performing here is we're taking a box of beer, a whole carton, and we're saying what is the probability that the average volume of beer in this box is larger than 340. Okay, so that's the difference. We're saying, what's the probability of a whole box having an average volume larger than 340? And then here you're saying, what's the probability of one individual beer? So if you think the mean is 335, you've got to have quite a few beers that are above the expected volume. And so that's why the probability of it is so low. So let's articulate the significance of that, because it says, state the significance, why is it different from A? So let's write that down as best as we can. So, part C, what's the significance? This is the probability of a whole carton of beer having an observed mean volume larger than 340 mils. Okay, so that's the significance of it. Why is it different? In part A, that maybe that best exemplifies the difference. So, part A, calculation for a single beer to be larger than 340. Part C is about the whole box of beer, the average of them being larger than 340. Okay, so, but just beware, it's not about the whole box having a volume larger than 340. It's about the mean, the observed mean of the whole box having a volume larger than 340. Okay, so very precise with our language there. Excellent central limit theorem. Let's give it a go.